Thank you everyone for attending. Good morning, good evening, everyone. Thanks for joining this ROS2 Embedded Working Group meeting today. This is the document that I will share with you through the meeting notes that we will follow today. So this is our 18th meeting in this working group, and this document recap the follow-up of last month's contributions. So we have the micro-ROS live code demo with field-oriented control from Felipe Neves from Expressive. And then we had a new feature of Wi-Fi transport available in the Renesas microcontroller family, presented by Pablo. And also we have this PowerPoint presentation about ROSRider and the micro-ROS proposal that will have a follow-up also in the agenda for this month. So what we plan to introduce today is three main topics. So first, Pablo will start by introducing the first port of micro-ROS to a Texas Instrument microcontroller. We have here a small setup to show up. Then Pablo will also provide an update of the status of ROSRider and the challenges of using micro-ROS in only 32 KB of RAM. And finally, I will make a presentation. It's a brief presentation that gathers like the whole life of micro-ROS, basically, from a high-level point of view. So it will be 10 minutes. You will learn where the micro-ROS framework is coming from. It is coming from a European funding project, and how this is transitioned through the community and through the market until today as a reliable and complete framework that is now being driven by the market itself and the needs of the companies. So it is not an R&D project anymore. So there will be time for questions and answers at the end of each presentation. If you wish to treat any further topics, please add it in the miscellaneous section of this document at the end of the agenda, and they will be treated afterwards. Okay, so I think we can get it started.
Yeah. Okay, so I'm going to share my screen. Can you see it okay? Yeah. Okay, I'm going to talk today about a couple of topics that are completely related. We have a new port of the micro-ROS stack on top of a new series of microcontrollers by Texas Instrument. And we also have an update on the ROSRider status of the micro-ROS port. Both of them are completely related because we have port micro-ROS to the MCU that ROSRider is using. And leveraging this work, we have port micro-ROS to a series of development board that Texas Instruments provide with a Cortex M4 family of microcontrollers. This is the evaluation kit that we have used. We have one of them here, and we have a set of normal features in an MCU. They also provide this development board that is called a Launchpad, and the microcontroller is this one, TM4C, etc. It has normal characteristics, but the most important one is that it only has 32 kilobytes of RAM. For those of you that have worked with micro-ROS, you know that fitting the whole RMW configuration in 32 kilobytes of RAM, it's quite complex. We had to reduce buffers and all the things in order to fit in this RAM size. But we will see that later. We have prepared a repository that is called micro-ROS app for Texas Instrument Tiva C Series. And here you have some instructions in order to build a micro-ROS environment in this development board. The most important thing is that this is a bare metal approach where we do not have any kind of RTOS, and we rely completely on the SDK, the software, the application development kit that Texas Instrument provides. Using this SDK, we will write transports and we will write other kind of timing functionality that micro-ROS needs. So you have here the link for downloading the software development kit, and then it's just a matter of making make in the project folder and building all the thing together. Along with this repo, we have a super basic application that we are going to see right now. So let me show, I am in the correct branch, yeah. So let me show a couple of things that are interesting about this port. The first of them is that we are using a bare metal system, but moreover, we are using the nano version of the new lib. That means that we have a super reduced libc environment where, for example, we do not have any kind of syscalls, even we don't have any kind of heap at linker stage. So, for example, we are going to handle the micro-ROS dynamic memory using a custom allocator that I'm going to show later. As you can see here, for example, we are implementing all the syscalls, just returning errors because we don't have support for the complete libc. In fact, the most important one is this one, the SBRK, that points us that this system do not have any kind of dynamic memory approach using the system heap at linker stage. That means that we cannot use malloc. So how is micro-ROS using the dynamic memory that it needs in order to initialize itself? Well, here we can see that we are creating this is a typical approach in micro-ROS, just setting custom allocators and using this functionality of RCutil to set the custom allocators just in the function of micro-ROS. And the first thing that we are doing is setting some custom allocators. Let's take a look on these allocators. And as you can see here, we have taken a super basic approach where the memory it's only provided. We are not able to free memory. Always the allocate function will retrieve a pointer inside of this static buffer that is, of course, aligned to 4 bytes, because in ARM architecture, you need memory to be aligned at 4 bytes. And we are just returning the pointer. But we are not able to deallocate anything. On the other side, for example, we can remove all the things from the heap. We can just reset the pointer. That means that micro-ROS is going to be able to allocate, but not able to deallocate. We are going to be in charge of deallocating the whole heap. This is interesting because this is an approach where an user can see how the dynamic memory is handled in micro-ROS. We have here all the control of the dynamic memory that micro-ROS uses, because we ensure by setting this syscall to a null pointer that the system is not going to provide any memory block using malloc. All the dynamic memory that micro-ROS uses are taken using this functionality. I think that this is quite interesting. In the same way, the system do not have any kind of clock get time functionality. So what we are doing here in this bare metal system is just using a tick count. This variable, this Win32 variable, is increased in the systick handler that is in fact the actual interrupt for the systick of the ARM core. So here we are incrementing here we are incrementing this variable and just implementing a function to provide micro-ROS with a timing functionality. Here we are calculating how many seconds and nanoseconds have been elapsed from the bot of the system. In the same way, for implementing the transport, in this case, we are using a serial on top of an USB port and USB-C DC transport, and we are implementing it in a really basic manner using the API that the Texas Instrument SDK provide to us. We have just this USB buffer write, and we have this USB buffer read. With this, we provide micro-ROS with the transport interface. You should know that we can set this transport using the RMW set custom transport, and here we can see what are we doing in order to provide the micro-ROS stack with the transport. Always, this is a serial transport, so we are using the framing. The framing is enabled. And finally, well, let's take a look on the micro-ROS application. This is a really basic micro-ROS application where we are creating a node that is named Tiva node, and we are also providing creating a publisher and a timer. This timer is going to run every 20 milliseconds, and in the timer we are going to publish just an integer, a super basic micro-ROS application. But I would like to show you how are we handling the disconnection of the micro-ROS agent here, because this is a common topic in the micro-ROS community that everybody is asking always what happens if the connection between the client and the agent is lost. How we can like re-enable this connection and handle these situations where the client cannot reach the agent. Well, we have implemented here a basic state machine that have 4 states. The first of them is waiting agent. Then we have an agent available. We are connected to agent, or the event where the agent is disconnected. Well, all this state machine is traveled by means of pinging the agent. When the micro-ROS client do not have any kind of access to the agent, it will keep just pinging the agent with a timeout of 100 milliseconds, one retry, and we will check if this functionality, if this function returns an OK. If this function returns an OK, means that the agent is available for creating our micro-ROS entities. So in the next step of the state machine, we are going to init the micro-ROS entities. This init function is just the common micro-ROS node initialization, the common publisher initialization, and all the things that we are used to, also the executor. Okay, so if we are able to create the micro-ROS entities, we can say that the state machine is in the state of agent connected. When we are connected, what we want to do is to spin the executor. So here we have this RCLC executor spin for 100 milliseconds in this case. But also we want to check if the agent is still available. So I have this magic macro here in order to run this statement once every 200 milliseconds, but this is not important. The important thing is that we are pinging the agent in order to check that the agent is still alive. Okay. What happens if the agent is not alive? If the agent do not respond to the ping, that the thing that happens is that we are moving to the agent disconnected state where we are finishing the micro-ROS entities. Well, this is a really important stage because in the finalization of the micro-ROS entities is where micro-ROS release the dynamic memory that it has allocated in the creation stage. So if you do not finish the micro-ROS entities properly, probably you will have a memory leak. In this case, because we have a super custom allocator, a super weird allocator where we are allocating the things in a static buffer, just we are freeing all the heap. Here we are releasing all the memory that micro-ROS can have allocated along the creation stage. And that's all. We can see now a demonstration of this working, because I think that we have achieved a really good performance regarding, for example, the timers. All the system works pretty well, pretty consistent in terms of execution. So I'm going to open here a micro-ROS agent, and we can see how the micro-ROS client just connects to the micro-ROS agent. We can do here a ROS2 node list. Well, let's first reload the demo. And now we can list, and we can see that we have this node named ROSRider. Well, this is not the node that I wanted to show. I'm going to reset the micro-ROS agent, reconnect the board. Okay, it's all ROS2 node list. Well, what's happening here? I think that I have the firmware of the ROSRider flash here, but maybe we can do ROS topic list. Well, I have the wrong firmware flash. Well, so let's continue with the well, let me check if I can do it here. Make flash. And now Tiva publisher. Here we can see that we have a node, ROS2 node list. That's it. That is Tiva node at the same name that we have provided here. I have just replaced the firmware because I had another version. And now I can do ROS2 topic list. We can see what is happening in Tiva publisher, ROS2 topic echo of this one. And one interesting thing here is that what happened, for example, if I close the agent. If I close the agent, the publication stops, and I can reopen the agent, and it just continue publishing because of this state machine based on the ping feature that I have shown. And another thing that I wanted to show is that we can check, for example, the rate of this publication. And it's really precisely 50 Hz, because we have set our timer to 20 milliseconds. Okay, and basically this is the basic explanation of what we have been doing with the Tiva C board of Texas Instruments. And now I'm going to change the branch in order to show you the approach that we have been taking with ROSRider. First of all, for those of you that didn't came to the last embedded working group, ROSRider is this board that features the same MCU of this launchpad board from Texas Instrument, and this board is designed to be like a common interface for ROS for interfacing with motors that have encoders. Here you can connect your encoders and your motors, and this board will expose you the required interfaces for moving the motors and doing all the operation need to have a differential drive robot, as you can see here. In general, here in features, we can see that the board will have a couple of subscribers, one for controlling the effort of each wheel, of each motor, and also it is going to be publishing the state and the position, state, the velocity, all the information required of each motor. Also, this is also really important because the board will have a set of parameters that will allow the user to configure important things about the motors and the configuration of the robot. For example, you can configure the wheel diameter. So you can say to the board that your differential drive robot configuration have 20 centimeters between wheels, and it will make all the calculations in order to operate the robot. Also the base width, the current limits regarding the motor drivers, and all the things that are related to this specific hardware, and all the things that this hardware needs to drive the motors. In the same way, I have a pre-built image in the other board, in this ROSRider board that the designer have sent to us. And now I'm going to show a little bit of the application. First of all, let me connect the other board. I change the USB CDC, but in this case, the power of the board is provided by a source supply. Okay, so here we are. In this case, we are creating 3 publishers, two for left wheel position and velocity, and 2 for right wheel. We are also creating a timer for publishing this information. We have also a couple of subscription in order to receive the control effort that we need to apply to a certain motor, maybe the PMW DATI or anything that can be related with how many voltage we should apply to a motor. We also have here a diagnostic publisher that we will see at the end. Here I am printing just information about how many stack, heap, and how many, and some voltages and on some things, and a really basic approach. We using a string. And then also we have a parameter server with all the parameters that we have seen in the web page. Finally, we are creating the executor, adding the timer, the subscription, the parameter server, and an additional timer. This timer is important because if we go to the application, this was the micro-ROS creation functionality, but here we have the main functionality. We can see that we have a lot of functionality that the creator of the board have provided to us, that the functionality for initting all the systems and connecting to all the devices that are on board, for example, using E2C or initializing the EEPROM, all the things that the board needs to do. But here we have our micro-ROS application with its allocators and with its custom transport and with the same state machine that I have shown to you in the other demo. Basically the same thing. But what is happening here? For example, let's see the callback of the left control subscription. When I receive a message, I will set the power of the motor to that value. But I don't want the robot to be moving if it is not receiving any control command. The control command needs to have a certain rate. So I have implemented here a sort of a deadline QoS for the micro-ROS topics using another timer. We can see that well, I don't have any motor connected, so we are going to see it using the LEDs. When I receive a command for any of the 2 motors, the right or the left one, I will set the LEDs to green. And more important, I will reset the deadline timer. What happens if the deadline timer occurs? If the deadline timer callback is executed, I will stop the motor and I will set the LEDs to red. In that sense, it's important to know that the deadline timer it's configured to execute every 100 milliseconds. That means that I need to publish a command to the motor faster than 10 Hz. So let's take a look on that. I'm going to stop the timer. I'm going to check that I have available my ROSRider node. I can do ROS2 node info for the ROSRider, and I can see that we have these subscribers. So we are going to publish to this one. To this topic, the type is std messages int32, and for example, we are going to publish a 10. It doesn't matter because we don't have any motor, so, and the rate is going to be 30 Hz. In that case, we can see how, I don't know if you can see the webcam, but the LEDs are green now. That means that we are receiving the data at the rate that we want to receive it. And the deadline timer callback is never being executed because it's always being reset at these points when we receive any kind of control on the comments. What happens if we do not receive anything? The LEDs will turn red again. But if we receive topics at 3 Hz, for example, we can see how the motors will enable and suddenly they will be disabled because the deadline timer callback. In this case, we can see the LEDs like turning red and red. When they are green, the motors are enabled, and when they are red, the motors are completely stopped. This is an implementation that we have done for that. And another thing that I wanted to show you is the parameters that we have prepared for this ROSRider micro-ROS implementation. We can check them here. We have done an approach using X macros, and we have 14 parameters. In fact, we have found that parameters are so heap hungry and they require a lot of memory. And we are, in fact, working in the RCLC in order to make them use less memory, at least when they are using micros, because they require a huge amount of heap memory in terms of embedded system. We will see later that this system with all these 2 subscribers, 3 publishers, and 14 parameters, it's using about 14 kilobytes of heap. Well, so we have these parameters, and in the C, we have the callbacks for each one of these parameters. These callbacks are going to be triggered when the ROS2 CLI change or modify any of the parameters. I have implemented only one of them, this wheel diameter parameter, but we can do here a ROS. I'm going to make this bigger. I can do here a ROS2 param list, and we can see that we have a ROSRider node with all these parameters. I can also do ROS2 param get this. I guess that we should do here ROSRider, the name of the node, and also wheel dia. And we see that the parameter by default is 6 centimeters. We can set the parameter, for example, to another value, 12.9. And when we retrieve it again, we can see the new value. What we are doing here, it's important because we are modifying a configuration of the hardware. And for example, we are recalculating the parameters. Let's take a look on the functionality that the author of the board have provided to us. In this case, when we modify the wheel diameter, we are recalculating this other wheel circumference parameter. So the hardware will behave in another manner. Other important thing that we have been trying, but this is not working yet, is the EEPROM functionality. This way, when I receive a new value for this wheel diameter parameter, I will save it in the EEPROM, in the non-erasable memory. So that means that when I remove the power of the board and I restart all the thing, the parameter will be saved in the non-volatile part of the memory. This is super interesting, but I don't know why this is not working. We should talk with Can, and let's check this EEPROM library to ensure that everything is working okay. But the functionality should be this easy. Here we are programming the value in the non-volatile memory, and then during the initialization, this value will be read. And this is a super nice way for configuring the hardware, just using the ROS2 param interface that you can see here. And that's basically all. I wanted also to show this diagnostic message. We are publishing in diagnostic, we are publishing just a string. And what we are publishing here in the timer, we can see here that we are just printing in a bare string the stack usage, the heap usage, a voltage, and current. For sure, we need to prepare a custom type for that has all the information that the ROSRider board can provide to us. But by now, we are just printing a simple string. So let's do a ROS2 topic echo diagnostic tick. And here we can see that we have configured 4 kilobytes of a stack, but the application is just using 2. This is the maximum stack usage. We are implementing, you can take a look on this because I think that this is interesting, but we are using a canary in the stack buffer, and then we are checking where is the position of the canary. For those of you that are used to FreeRTOS, this is the same way that FreeRTOS calculates in one of the 2 options that they provide. This is the way that they calculate the maximum usage stack. And on the other side, we are using almost 14 kilobytes of heap. We know this value because, of course, we have implemented the allocators here. So we just by means of checking the current pointer, we know how many bytes we have used in the heap. And finally, here we have a couple of values that we are extracting from the board API. It has like a global variable that is boost voltage and boost current. So we are also printing them here, but I'm not sure that this is being measured correctly. But mainly the micro-ROS interface and the functionality that we wanted to achieve, that is a hardware that is able to receive some data for controlling motors and to publish its state, because we don't have take a look on that, but for sure it is publishing the position of the left wheel. But the point is that with no motor, this value will be 0. So in summary, we have a board that receives control commands for moving motors, and also that sends feedback in terms of motor velocity or motor position. And also we have an advanced feature of micro-ROS that is the parameter server. In fact, we have 14 parameters that it's a lot, and we are using almost all the memory in the chip. But for sure, with these RCLC modifications, I think that we can save a lot of heap memory and maybe be around 6 kilobytes. In some tests that we did, we are in around 6 kilobytes, but this is not working properly yet. All the thing just using the micro-ROS timing functionality and a super basic state machine, and using ROS2 compatible interfaces. That's all. You have the whole thing, the whole code that I have shown here. The first one in the master branch, and the other in ROSRider app. I think that I need to push some more commits, because I have some parts that are local yet, but I will put all the thing here. You can take a look, and I think that this is a super good example of a bare metal micro system with a lot of functionality in a super small memory footprint. That's all.
Thank you, Pablo. We had a question from Jan here in the chat.
Mm-hmm.
So to avoid memory fragmentation due to deallocate and initialize every time the agent is connected and available again, could it also be possible to have a state machine which keeps the memory allocation from handles?
It depends on the memory allocator that you are using, and for example, in places where we are using FreeRTOS heap 4, that you know that FreeRTOS have like 5 implementation of heap manager. In the heap 4, they make this coalescence feature that if you release all the blocks that are at the end of the heap, the heap manager will put them all together, so you do not have a fragmentation. This is really interesting because micro-ROS will always allocate the same amount and the same block size, and the same amount of blocks with the same block size. That means that when you finish all the entities, all those blocks will be free, and the coalescence feature will make one block, and you will not have a fragmentation.
Yeah, first of all, it was really great to have the state machine in the first place, right? which is very very good to check that the agent is not available, and you are checking this and so on. And it was just a point of optimization, because actually when the agent becomes not available and becomes available again, I mean, is it really necessary to deallocate and allocate again? Because the subscriber and the timers will be the same, right?
Yeah, I know. It should not be necessary, but if you close the agent and if the agent is not available, you need to create again all the entities. I mean, there are like two possibilities. If the link is broken and if the agent have died. If the agent is died, you will not be able to reuse anything because anything is created. So you need to recreate all the thing. And using the ping, you don't know if the agent is not available because the process is died, or if the link is just broken.
Okay. Because I, we have been experimenting with, micro-ROS on an AUTOSAR-based platform, and there is just a, so to say, there's no heap, so there's just a stack.
Yeah.
And whenever we allocate memory, it's on the stack. And when there's no, so to say, it's not easily possible to, I mean, in the simplest version, to deallocate on the stack.
Yeah.
But I see the point, and it's already a great feature.
Thank you, Jan.
Thank you. Is there any further question? Okay, then. So now we should proceed and present the last topic of the agenda, but I'm afraid. Thank you, Cam. Excellent work. We cannot exceed the time. There's no enough time left for it. And also, we have a problem with the meeting invitation, and many people is missing here today. So in the interest of time, we will be moving this last presentation to the next month. So I'm going to check if there is any further topic in the miscellaneous section of the document. So nobody has added any further topic. Do you have any further question before wrapping up? Okay, great. So, well, thank you. Thank you for attending. And this recording is going to be online tomorrow, and will also be added to the document, or to the meeting notes. So we will be back next month with very interesting topics. So please stay tuned. And thank you, everyone, and have a good rest of the day. Thank you.
Bye.